Last episode, we saw that your neural network can be modeled as a graph, which, we'll show in this episode, can be viewed as a higher dimensional simplicial complex. So, what is a simplicial complex? Simplicial complexes, the object we're interested in studying, are built from simplices, the plural of simplex. A simplex is a generalized triangle, a triangle in any dimension. A zero simplex is a single vertex. A one simplex is two vertices connected by an edge. A two simplex is three vertices connected pairwise by edges with a single face, in other words, a triangle. A three simplex is four vertices connected pairwise by edges joined by four faces, which are filled in to form a solid, a tetrahedron. Let's try it in 4 dimensions. To build a four simplex, you start with 5 vertices. You then fill in the one-dimensional edges between the vertices, the two-dimensional faces between the edges, the three-dimensional solids between the faces, and, here's where it gets weird, you fill in the four-dimensional space between the 3D solids. It's hard to visualize. Generalizing that pattern for any number k, a k-simplex, which is k-dimensional, is formed using k plus 1 vertices. The k-simplex is made up of those vertices and all the space in between them, what's known as the convex hull. Remember from our episode on structural balance that a complete graph is a graph where each vertex is connected to every other vertex by an edge. Well, we can interpret complete graphs as simplices. The complete graph shows all the nodes and edges. Then we fill those in with two-dimensional triangular faces, three-dimensional solids, four-dimensional spaces, and so on. The complete graph on k vertices will form a k-1 simplex, so it's k-1 dimensional. For example, this complete graph on 3 vertices becomes a 2 simplex when we fill in the two-dimensional triangular face. This complete graph on 4 vertices becomes a 3 simplex when we fill in the two-dimensional triangular faces and the three-dimensional tetrahedral solid. A 4 simplex is difficult to imagine. It lives in 4-dimensional space. But this diagram shows the vertices and edges. A simplicial complex is basically just a bunch of simplices, possibly of different dimensions, considered as one collective unit. It's like an apartment complex, except the apartments are simplices. The individual simplices can be completely separate, like these pieces, or they can be stuck together by sharing a face, like these tetrahedra, or an edge, like this triangle and tetrahedron, or a vertex, like these. Notice that this intersection happens along an entire face, not part of one, like this. You can actually stick higher dimensional simplices together along higher dimensional faces, but we've already reached the limits of my visual imagination. Just as we can view any complete graph as a simplex by blowing it up into a higher dimensional geometric object, we can interpret any graph as a simplicial complex. Here's how. First, mark each complete graph. Notice that the complete graphs can overlap. This 3-vertex complete graph overlaps with this 2-vertex complete graph, but they don't collectively make a 4-vertex complete graph. Similarly, these two complete graphs overlap, and so do these. Now, to turn this into a simplicial complex, we just convert each complete graph into a simplex by filling it in. When two complete graphs overlap, their representations as simplices will share a vertex or an edge or a face, like these or these. A simplicial complex can take many forms. Unfortunately, we're limited to animating them in 3 dimensions, but the mathematics works in any dimension. Simplicial complexes are often studied in a branch of math known as algebraic topology. Topology is often referred to as rubber sheet geometry. It studies shapes, but not in a rigid way. The topologist is free to bend and stretch shapes without puncturing it or contracting any holes. They study the properties of shapes that are preserved by this flexible motion, such as how many holes of each dimension a shape has. As Robert Grist put it in his article, Barcodes, the Persistent Topology of Data, algebraic topology offers a mature set of tools for counting and collating holes. I realize that sounds a bit funny at first, a branch of math devoted to holes. But these tools, which have been developed for centuries in pure abstract mathematics, are suddenly finding applications. Much of the research within pure mathematics has focused on developing and fine-tuning topological invariants, which are numbers that we assign to a shape, or simplicial complex in this case, to learn something about its global structure. The first is the Euler characteristic. Here was Euler's original observation. For any three-dimensional convex polyhedron, that means a shape like these without any holes or inward pits, the Euler characteristic, which is the number of vertices minus the number of edges plus the number of faces, is always 2. Try it. Here's a cube and a tetrahedron and a giant awkward shape without a name. They all have Euler characteristic 2. Let's focus on the cube. What happens if we take a chunk out of the center? So now it looks like a torus or hollow donut. The Euler characteristic drops to 0. What about another chunk? So there's 2 holes in the torus. Well, the Euler characteristic drops to -2. You can see that the Euler characteristic tells us something about the topology of a surface. We can easily generalize this definition to give the Euler characteristic of a simplicial complex in any dimension. Let's say your simplicial complex is made up of simplices ranging from 0-dimensional to 4-dimensional. Then the Euler characteristic is the number of 0-dimensional vertices minus the number of 1-dimensional edges plus the number of 2-dimensional triangular faces minus the number of 3-dimensional tetrahedral solids plus the number of 4-dimensional spaces. Another important topological invariant are Betti numbers. Betti numbers are a sequence of numbers which indicate how many holes of each dimension an object has. Let's see some examples. Here's a torus. The first Betti number counts the number of 1-dimensional or circular holes. So there's 2, 1 along the longitude and 1 along the meridian. The second Betti number counts the number of 2-dimensional holes, which for the torus is 1. The contents of the torus are a 2-dimensional hole. What about this 2-hole torus? Its first Betti number is 4 and second Betti number is 1. Here's one more example, this time using a simplicial complex. For these 2 hollow tetrahedra joined at a common vertex, the first Betti number is 0 and the second Betti number is 2. Similarly, by some giant stretch of the imagination, the third Betti number counts the number of 3-dimensional holes, the fourth Betti number counts the number of 4-dimensional holes, and so on. There's also a 0th Betti number, which counts the number of connected components a shape has. So 2 in this case, and 1 in this case. Euler characteristics and Betti numbers, and their parent concept homology, are an essential part of the algebraic topology toolbelt, the one that counts and collates holes. They're particularly important to the study of simplicial complexes, which is how we're modeling the brain. In other words, the connections between your firing neurons can be viewed as a high-dimensional simplicial complex, and the tools of algebraic topology will allow us to study the properties of that structure, to determine its shape. And, as we'll see on our next episode, the final in our Brains mini-series, this may be the key to understanding the mysterious connection between neurological structure and function.